Okay, today's module is looking at Ohm's Law, one of the most famous laws within inside electrical physics, and it's interesting how this law here is used to derive so many other laws. So we want to be really familiar with it, and we want to be able to solve problems using it. Okay, so that's one of the objectives for today. Now we want to have a look at this idea of ohmic versus non-ohmic conductors, and we want to be able to interpret graphical representations of Ohm's law and non-ohmic conductors, and we want to use this to find what the resistance is in both ohmic and non-ohmic conductors, and we also wanted to work out the uncertainty in this resistance, and we need to investigate resistance across ohmic conductors. So you'll get the general gist of it, but let's start with some algebra. Okay, so because we have a three variable equation again, where one is the product of two of the others, we have a triangle. And so we can, if we want to find the voltage and we're given current and resistance, we use V equals IR. If we're trying to find the current, we can take voltage and divide it by resistance. And if we're trying to find the resistance, we take the voltage and divide it by the current. Now, let's have a bit of graphing practice for these. So pause the video and try and graph voltage versus current, given the law before, voltage versus resistance, and current versus resistance. So this is graph 1, graph 2, graph 3. See if you can sketch them out just on your book, and it's just looking at the proportional and inversely proportional relationships. So pause the video now and give them a go. Okay, great. So we're back and we're looking at what these relationships would look like. Well, voltage versus current. What we know is if the voltage goes up, the current also goes up. Okay, maybe I should draw V equals IR, and that's a horrible color for it, but we'll remember that. So if voltage increases, current increases, and resistance stays the same. So that's a proportional relationship. So we should see a nice proportional relationship going through the origin. Now, the next one, voltage versus resistance. Let's draw this in white so we get a better look. So V equals IR. So we got here voltage. If voltage goes up, okay, at a constant current, then the resistor might go up. Now you're probably asking, how can the resistant go up? There's things called thermostats, and there's other things called variable resistors, which will change. Okay, so if we increase the voltage, I'm going to change back to a blue pen. If I increase the voltage, the resistance would also go up if we kept the current the same. It doesn't happen all the time. It has to be a special situation, but that is what the relationship suggests. Now the last one is if voltage is the same, we have an inversely proportional relationship. So if I goes up, R must go down in order for voltage to stay the same. And so inversely proportional looks like this, where that shouldn't actually touch the y-axis, and that won't touch the x-axis either. And basically what we see here is as I increases along here, the resistance decreases, which is what we would expect. So hopefully you got those three graphs correct and you understand the visual representation of Ohm's law. Let's have a look at some examples now. So in this particular example, we have a potential difference of 3 volts is applied across a piece of wire. 5 amps of current flows through it. That's quite a lot of current. Calculate the resistance of the wire. So we just manipulate Ohm's law to get it resistance as the subject. Substitute in for the 3. Voltage is 3, current is 5. Put it in, we get 0.6 ohms. Let's try one for ourselves now. Pause the video, give this one a go, and come back for the answer. Okay, so hopefully what we realize here is we're looking for the resistance. And so the resistance is equal to V over I. Here, we are given a current of 10 amps and we are given a voltage of 240 volts. Calculate the resistance. 240 divided by 10, we're going to cancel those out. We get left with 24 ohms. Using Ohm's law now to work out current, and we want to express it in milliamps. So a 100 ohm resistor is connected to a 12 volt battery. Calculate the current that would flow through the resistor. Start with V equals IR. Rearrange to the form that we want it in, with current, the unknown, as the subject. Substitute in the value for the voltage, 12 volts divided by a 100 ohm resistor, gives 0.2 amps. Now, milliamps is 10 to the negative 3, okay? So in this particular case here, what we want to make sure is we put 10 to the power of 3 and then the prefix milli. So the milli is 10 to the negative 3, and 10 to the 3 multiplied by 10 to the 3 is just 1. So we can do that. So this is what's actually happening here is they're saying, well, I'm going to take something which is 0.12. I'm going to multiply it by 1, which is 10 to the 3 times 10 to the negative 3. That's 1, okay? And we have amps. But this here is a prefix milli. And so we get left with 120, okay? 0.12 times 10 to the 3, 120 milliamps. Let's pause the video here and give this one a go. Okay, so you're back. Let's try this. And so once again, in this particular case, we want the current in milliamps. So we put current is equal to voltage divided by resistance. That gives us voltage of 240. We're going to be dividing it by 25. And if you put that into your calculator or work it out in your head, you get that is 9.6, and that's amps. Now, that's quite a lot of current, and expressing this in milliamps is not necessary, really, but we're going to do it. So we take the 9.6, multiply it by 1, which is times 10 to the 3 times 10 to the negative 3 amps. No, that becomes 9.6 times 10 to the 3 milliamps, and that becomes 9,600 milliamps. So the last one that we want to do is just work out the potential difference, and so we don't have to rearrange the equation at all. So the current of 0.25 amps flows through a 22 ohm resistor. Calculate the voltage across the resistor. All we're doing here is substituting in for current 0.25 amps, resistance 22, and we get a potential difference of 5.5. Pause the video here, give this one a go, and come back for the answer. Okay, so hopefully what we see here is we're just using V equals IR, substituting in for the values given, which is 700 milliamps, so 700 times 10 to the negative 3 amps. I'm not going to express it as milliamps, I'm going to put it back into SI units. And then we're going to multiply this by the resistance, which is 5.7 ohms. And the potential difference of what we'll see when you put this into your calculator, you can just put it in with the numbers, and we would get 0.7 times by 5.7. We're looking at 3.99, and this is volts. And because this is given, this is given to 4 significant figures, you have to count that one because otherwise they wouldn't express it as decimal. But the smallest one is 2 significant figures, so we should round that off to 4.0 volts. Okay, now this is a little bit more of a difficult one. So what we want to do here is using Ohm's law to calculate the resistance, current and potential difference. So on an Ohm's law ohmic conductor, we have the following relationship, V and I. And so what we see is that it's proportional to. Now, these values here tell us nothing. They give us absolutely nothing. So we need to use two of the number values here. All we need is 4, okay? because if voltage doubles, so will the current. Okay, and then if this one goes up by a factor of 3, this one must go up by a factor of 3. So we want to work out this, the proportions correctly. And so one way of doing that is just by saying here, like they did, what we know. Let's do which question we were working out the current first down here. All right, I would do this slightly different. I would say that 2 over 0.25 is going to equal 4 over current 1. All right, now we want to rearrange for current 1. We get I1 then is going to be 4 times by 0.125 divided by 2, which is 1/2, which is 0.5, and we're expressing this to two significant figures, and so we get 0.5 amps. Okay, so I always would start with this equal rates or ratios, because we know in this case here that V over I is going to be the same for an ohmic conductor, no matter what. So V1 over I1 is going to equal to V2 over I2. And so we can use the exact same idea down for this last one. And what we would say here is that, well, 2 over 0.25 is going to equal to V2 over 0.75. So that means that V2 is going to equal 0.75 times by 2 over 0.25, which we can see is equal to 6 volts. And it's the same answer as what we had before. Okay, the other way you could do it is exactly what I spoke about before. If this has gone up by a factor of 3, which we can see it's done that, this must also go up by a factor of 3. If this one has doubled, then this one must also double. But if you use this method up here, you'll always get to the right answer. So let's try one of these for ourselves. Pause the video and come back for the answer. Okay, welcome back. So I'm going to use the equal resistance ratios. So what I know, if we want to work out what I1 is, determining I1, what we want to do is put it in one of those equal ratios. 3 over 0.2 is going to equal to 9 over I1. Yeah, rearrange for I1. So I1 becomes 9 times by 0.2 over 3, which is going to be 3 times 0.2, which is 0.6, and we're looking at amperes. The second question, we're looking for V2. Once again, put it in so this time I'm going to go V2 over 0.8 is going to equal my 3 over 0.2. Multiply both sides by 0.8, and I get 3 times 0.8 over 0.2, which we can see is going to be 12 volts. So that's the answer to those ones there. Now, this is what an ohmic resistor would look like on a graph. We've spoken about this. Okay, so as voltage increases, okay, current increases proportionally. What does the gradient represent? Okay, think about it. Pause the video, think about it, and see if you come up with the answer. So the gradient is going to equal to the change in I over the change in V, which is just I over V. But Ohm's law states V equals IR. So I want to get I over V. So I divide both sides by V, and I get 1 is equal to I over V multiplied by R. And now I want to get rid of the R because I've got my IV, and I get that I over V is equal to 1 over R. So if I was to work out the gradient here, on this graph, just by taking 2 points, any of these points, okay, what you would realize is that that is 1 over the resistance. So we could potentially work out the resistance of this particular resistor. And let's do that for a bit of fun. Let's not use blue. Come back to my white pen, and what we see is we're going to take, we can take the whole way down up to the top right hand corner there. And so the gradient I over V is equal to 4 over 8, which is 1 over 2, or 0.5. So then the resistance, 1 over the resistor, is equal to 1 over 2. So that tells me that R must equal to 2 ohms. And this is only for ohmic resistors where we have a proportional relationship. What we look at is a thing we talked about, or asked the question last time, how would temperature affect resistance? And temperature has a big effect on resistance, because if you use my corridor example, okay, here's some particles in here, and they're going to vibrate really fast, okay, because temperature is kinetic energy. So these molecules here are moving back and forth. Now they could be molecules, they could just be atoms, whatever they are, they're moving all the time. That makes it extremely difficult for an electron who wants to pass through. So say there was the negative potential difference at this end and the positive plate at this end. This electron wants to go this way, but it keeps having collisions with all of these moving particles. It's very hard to move past something that's moving quickly. So we get an increase in temperature. So as temperature goes up, okay, resistance also goes up. But it's not a proportional relationship, okay? It's more of a squared root relationship or a power relationship. But we don't need to know that. All we need to know is that temperature, as temperature goes up, resistance also goes up. And this shows this here, because here what we see is the slope is getting less and less as we go along. Okay, as we get more current, we get less of a slope, which you would think that means less resistance, but it doesn't. Remember here that the slope only represents 1 over resistance. So as the slope is getting less, that really is showing us that the resistance is getting larger. Okay, and so we don't use slopes to work out the resistance of a non-ohmic conductor. What we do is we choose 2 points. Okay, so if I wanted to work out the resistance of this particular light bulb at this point here, okay, I would take the resistance is going to be the relationship between V over I. And so I can read V off my graph as 7 and current to be 3.5. So at this particular spot here, there's a 2 ohm resistance. Whereas if I took another point, if I took the point down here, resistance is equal to V over I. I read off, my V is 1, my current is 1, so I have a 1 ohm resistance at this particular temperature, or for this particular current. Remember, this is when everything starts interrelating, that current is directly related to temperature, because it's directly related to kinetic energy, because it's the flow of electrons. Okay, so everything's interrelated, and as we get a larger current, we get more resistance, which flattens the graph off, and the only way we can find resistance on a non-ohmic conductor is when we actually use the values for the certain points. Okay, because it's specific to that current. Let's try an example of this. So here's our graph. Okay, calculate the resistance of the light bulb when the potential difference is 5. So we need to go up and we need to read that off. Okay, so the resistance is V over I. We've already said that V is 5. We look across, we see current is 3. Rounded to 2 significant figures, we have 1.7, and there should be an ohm symbol there. Let's try one for ourselves. Okay, so here we got at 240 60 watt light bulb has IV characteristics shown in the graph. Calculate the resistance of the light bulb at 175 volts. So 175 volts we can see is here, which is at 225, and this is 175, and so the resistance is going to equal V over I, which is 175 divided by 225. And that's milliamps. It's a bit of a trick there. So we want to times that 10 to the negative 3. And what we get is 175 divided by 225 negative 3. And we get that that's going to be 777. Rounded to 3 significant figures is 778. And that's ohms. Okay, so just be careful of the scale and read the question properly. All right, so as a summary for the lesson, lots of maths. What we want to know is that Ohm's law describes the relationship between current, potential difference, and resistance. Yeah, conductors that obey this law at all times are known as ohmic conductors. Ohmic conductors have constant resistance, okay, and the gradient, you can use gradient analysis to find this. The resistance of non-ohmic conductors varies for potential differences, meaning, that's actually the current that affects the temperature, and the kinetic energy moving makes it harder for the electrons to get through, so it increases the resistance. And to find that, we need to use a graph, and we need to use a specific spot in a non-ohmic conductor. Okay, that rounds up the lesson. Thank you.